Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Bridge Design Innovation Using Weathering Steel. My name is Amanda from Engineers Australia. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders, past, present, and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, BlueScope. BlueScope is a provider of innovative steel materials, products, systems, and technologies, headquartered in Australia, with operations spread across North America, Australia, New Zealand, Pacific Islands, and throughout Asia. BlueScope is one of the world's leading manufacturers of painted and coated steel products, and with strong expertise in steel, they provide vital components for houses, building structures, and more. With more than 160 operations and sales offices across 18 countries, they employ over 14,000 people and serve thousands of customers every day, including engineers, architects, and specifiers. BlueScope's strong partnerships and networks are built on their recognised product brands such as Colorbond Steel, Zincalume Steel, Galveston Steel, and TrueCore Steel. Today, we will hear from 3 speakers, followed by our live audience Q&A. And as always, I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our moderator for today, Georgina Baxter, who is an Associate Bridge Engineer at Aurecon. Please welcome Georgina Baxter.
Thank you, Amanda, and welcome again to our viewers. I'd like to welcome our first speaker for today, David Talbot. David is a Principal Engineer with Arcadis and has a wide range of experience across bridges, rail, highways, and general civil structural engineering. David has contributed to all stages of major and minor design consultancy projects, from strategic route planning through to detailed design and construction supervision. Please welcome David Talbot.
Thank you for that introduction. Today in this webinar, we will be talking about weathering steel, and in particular for the bridge design that was done for the Berry to Bomaderry Princess Highway upgrade. My name is David Talbot. I'm a Principal Engineer with Arcadis, and I'll be running through the project overview, design and engineering aspects, and then I'll be handing on to other speakers to talk about the fabrication and construction aspects for this project. So here's just a brief agenda. So as I said, I'll be talking initially just about the project site, and I'll do a little bit of a slide on what is weathering steel and just some of the aspects of that material. I then just want to touch on the design and engineering aspects. So in particular, the sort of design for strength, serviceability that you do for any steel. And then in particular for weathering steel is the detailing considerations that need to be followed and understood. And that's of the most import with weathering steel. So first of all, the project summary. So the project was the Berry to Bomaderry upgrade, so a couple of hours south of Sydney. It was all done by Arcadis as the lead designer, and it involved about 10 kilometres of a highway upgrade, so that's duplicating and separating the 2 carriageways. So with that, I've just listed out a few things there that you can see, pavements, traffic, etc. But the most important one for me, obviously, is the structures. So there were a number of bridges, retaining walls, culverts, and today's topic is on the 2 weathering steel overbridges. So this is a map that you can see on the right there. I've just highlighted in yellow the 2 bridge sites. So the northern one is Strong's Road, and then the southern yellow highlight there is at Pestil's Lane. So the Strong's Road bridge is a single span 55-metre bridge, and that was on about a 20-degree skew. The bridge on Pestil's Lane is longer, just due to the site topography, and that's comprised of 3 spans, so a 30-metre back spans and then a 40-metre main span over the new highway. What is weathering steel? So weathering steel is like any steel, but just with a couple of little tweaks. So it's a steel alloy. It contains trace metals, so it's only about 2% of the makeup. But those trace metals help to form a surface coating when it rusts. So the surface coating is called a patina, and this patina, due to those trace alloys, is far better than normal rust. So any steel rusts normally when exposed to water and oxygen, but typically what happens is that rust coating is quite brittle and porous. So over time that rust forms and then detaches, and then fresh steel is exposed, a cycle continues on. So with weathering steel, it's a similar sort of process, but the rust that forms, or the patina that forms, with those alloys form a stable protective coating. And this coating is a lot stronger, a lot more durable. It adheres to the base metal and it is much less porous. So effectively, it's steel that forms its own paint coating. So just to touch on the corrosion, and particularly the corrosion allowance that we made for these Berry to Bomaderry projects. So weathering steel needs sort of cyclic wet and drying to form properly. So it's not suitable for use in every location. It's also subject to normal other durability considerations. So the patina doesn't form well with high chlorides or other environments that are quite aggressive. So I guess first of all, you just need to assess your site and see if it is suitable for weathering steel. So weathering steel can be, when used in the right locations, quite an attractive product, very low maintenance and economical, particularly for the long term, just because of that reduced maintenance requirement. So for these 2 bridges on the Berry to Bomaderry project, a 2mm loss of section was considered over the 100-year design life of the bridge. And that 2mm is a fairly conservative number. Once the patina forms correctly, then the corrosion rate, the long-term corrosion rate, is very small. And typically it takes about 8 years for the patina to form completely. So just a few benefits of weathering steel. So as I mentioned there, really the biggest benefit is that reduced maintenance. So because you're not out there painting and repainting, there's a huge saving both in cost and safety. So you can see there, I've just listed out a few little bullet points. So the economic solutions, that whole of life or life cycle cost. With any steel bridge, as opposed to say an in situ concrete or concrete, then there is the savings in the rapid construction. So being able to fabricate steel girders off-site and then bring it into place and allow that speedy construction. I've just also listed out there some of the current Australian standards. So the main one for the design aspect is AS 5100.6, so that's part 6 of the bridge code, and that lists out a whole bunch of design and detailing requirements. Then the material specification, so that's the AS NZS 3678. So that's for the actual material, the weathering steel material itself. AS NZS 1554 for the welding. AS NZS 5131 for the fabrication and erection. And then I've also just mentioned the Transport for New South Wales QA specification, so that's B201. And that has some particular requirements just to supplement those codes for steelwork used in bridges. So next is to touch on the actual maintenance aspects. So with a weathering steel bridge, you're really just looking at periodic inspection and cleaning. So you want to be making sure that that patina is forming properly and that you're not having any other issues. So that makes weathering steel bridges ideal where you're over a major freeway or some other hazard that makes access and future painting of steelwork very difficult or dangerous. So where you really want to reduce that maintenance requirement, that's when weathering steel really comes into its own. The patina, as I said, takes about 8 years to form properly, and that ages and darkens with time. So you might see some of the photos now, it's quite orange, quite bright, but yeah, over time that'll darken and tends to sort of blend in with the environment, and I think looks quite good. So the next item that I just want to touch on is just some of the design and the engineering aspects for this project. So firstly, the design, and I guess the biggest question is, why was weathering steel adopted? So the solution that we ended up with was a steel trough girder with a composite reinforced concrete deck. And the main driver for that was the span arrangement. So the requirement to have a clear span over the new highway. And this meant that, I guess, more of your standard or traditional precast girders just couldn't be used in this situation, just because in order to utilise the precast concrete for these longer spans, you'd be looking at sort of bespoke and very inefficient designs. So that's why we went for the steel bridge option. The steel also gave us a far quicker, more rapid construction time, being able to fabricate the girders off-site and then lift them into place. The skewed crossing that I mentioned at Strongs Road as well, so that was, it's not sort of pushing the boundaries as far as bridge skews go, but 20 degrees is still a reasonable number. And with steel, you can fabricate the steel, manufacture it to accommodate that skew a lot easier than you can detailing for concrete. So now the detailing aspects. And I guess this is where the weathering steel considerations really come in. So in terms of strength and other performance designs, so serviceability and fatigue, it's quite similar to any steel. So working through the Australian design standard, following that process as you would for any steel. The particulars that come with weathering steel are really on the detailing, and they're focused on the formation and maintenance of the patina. So as I sort of touched on a little bit earlier, the patina needs cyclical wet and dry to help it form evenly. So if it's exposed to fully saturated environment, or if it's exposed to a really dry environment, then that patina doesn't form properly. So what we want to try and avoid is any water dripping or any water ponding on any of the detailing elements. So at the time of this project, there was very little Australian standards or historical use of weathering steel bridges in Australia. So we lent on international best practice and international standards, in particular some of the guidance coming out of the UK. The current design standards, so the AS 5100.6 or Part 6 of the Bridge Code, that actually provides some corrosion allowances depending on your exposure environment, and then also the detailing, some of the detailing requirements and strength design requirements. Special mention, I guess, to the HERA Design Guide. That provides some excellent advice for best practice detailing, which is not, explicitly stated in some of the other codes. So finally, I guess from me, here's just a couple of little details that I just wanted to touch on that were used on this project. So the first one that you can see there is the drip inducer. So that was provided on the soffit of the concrete deck panels. The purpose of that is to intercept any water that might be on the underside of the deck and allow it to drip off before reaching the steel box girders. The next one is the grinding of welds. So having a smooth flush weld means that you don't have any potential for trapped areas where water might get caught on some of these welds. And it also provides a more attractive appearance, so you're not seeing sort of bulges or welds that are along the length of the girder. Lastly, the one that I just wanted to touch on now is the runoff. So for Pestil's Lane, which was a 3-span bridge, we have the piers. So we have 2 piers. And what you want to avoid, I guess, is any of the dirty or stained water that might come off the weathering steel bridges from spilling over the concrete piers and staining them. So for this location, we provided some fall and then a downpipe through the pier just to capture that dirty water so that we could minimise any staining. Thank you for listening. I'll now hand over to the other speakers who are going to talk about the fabrication and the construction aspects of this project. Thank you.
Thank you, David, for your input. I'd now like to welcome our second speaker for today, Andrew Sams. Andrew is the Quality Manager for Civic Mech Construction and Engineering and has over 20 years of experience in the welding and fabrication environment. Andrew has worked on some of Australia's largest mining, infrastructure, oil and gas, and marine and defence projects, and is currently a participating member of Standards Australia WD003 Committee, covering structural steel welding in Australia. Please welcome Andrew Sams.
Hi everyone, my name's Andrew Sams and I'm the Quality Manager here at CivMech Tomago. I've been with these guys for around about 6 years now and I was heavily involved in the Berry to Bomaderry project. Once we were awarded the project, we started the fabrication of the girders in around March 2019. The Berry to Bomaderry bridges were the first weathering steel bridges ever commissioned by RMS, which is now known as Transport for New South Wales. The contract was made up of two bridges, Pestil's Lane, which was 300-metre long girders, and Strong's Road, which was 355-metre long girders. BlueScope supplied all the weathering steel material, which was delivered over a 12-week period. And I think at the time it was around about a 6 to 8 week lead time on the material. There was regular contact with the mill and distributors on the forecast deliveries. And this really worked well with us so we could plan all the necessary resources for unloading at our Tomago site. We made sure that all the plate was stored inside the main workshop to ensure that the material was protected from the elements and also eliminated any issues of water ponding on the plate surface. It's really important about the ponding of water because you need to do this or to avoid this so you don't create issues to the patina, or also it can create unacceptable corrosion rates as well to the plate. For Pestil's Lane and Strong's Road, the external bracing had to be made out of strip plate as there was currently no weathering steel hot rolled sections manufactured in Australia. This is a bit of a slow process, but maybe in the future hot rolled section will be produced here. The bracing was fabricated to replicate standard 200 by 200 by 16 hot rolled equal angle and also a standard 310 UC. When tendering a unique bridge like this or a unique project like this, it's very important to understand the material that is required and the availability of that material. While we sometimes assume that the items are readily available, on the odd occasion they can catch you out. A good example of being caught out was sourcing of the weathering steel bolts. The procurement of the bolts posed a real concern for the project schedule. As we found out, the bolts were not manufactured locally. This meant we had to look to the UK and the US markets. We managed to source the weathering steel bolts from the US. However, there were minimum order quantities, and I think the availability was only in imperial and not metric, and also there was long lead times, which was approximately 12 weeks. The big sticking point was the bolts were not metric as per the original design. We had to go to the client to seek dispensation to not only accept the imperial bolts, but also accept the increase in the bolt diameter of the hole to suit the large imperial equivalent. That's just sort of a couple of examples of challenges in the procurement stage of the project. Once the material had arrived, we had to nest and process these plates into fittings. The profiling of the plate components was utilised by our own plasma bed, which is 40 metres long and has two cutting heads, a K3000 and a K4000. Our plasma has a reticulated water system which captures and filters out any smoke and dust created from the cutting process. Water also reduces the risk of distortion of the plate. In order to ensure the best outcome of the plate, we drained and cleaned the reticulated water to reduce the likelihood of any contaminants and ensure that the weathering steel patina was not affected. To process the fabricated sections, we also used our facette beamline. The beamline, it cuts, drills, scribes, all the items that are needed on the build. All items are uniquely identified in order to meet the B201 standards CC3 requirement. This meant that every single item, plate, section, bolt, nut, washer, had to be 100% traceable. So at any stage of the build, we need to know exactly where any item is on the bridge. For the fabrication, we used a unique engineered jig design in a way that assists us in a few areas of the build. The jigs are designed so that they cradle the webs and flanges of the bridge in its fabricated shape, which allows our boilermakers a relatively easy fit up. The jigs are also designed to shape the girder in their weightless geometry. The weightless geometry should directly translate to the final weighted geometry of the bridge once it's installed on site. And finally, the jigs also provide us the ability to use alignment aids, not use alignment aids or dogs and wedges on any of the external surfaces. Any temporary attachments welded to the external surface could directly affect the weathering steel's final patina and appearance. With the welding, we used a two-consumable method, which is specified in Australian Standard 1554 Part 1. All butt welding, which was on the external surface, was done with a combination of an ESAB 7100 wire, which is considered like a common carbon steel wire, and also a Lincoln 81 Ni2, which is a low alloy filler metal. The reason for the nickel wire on the external welds is to offer extra corrosion resistance and give a similar rusty appearance of the plate. I should probably note that there was a test plate welded up using the Lincoln 81 Ni2 a few months before starting the welding on the bridge, and the plate was taken down to where the bridge site was located and left outside to see how the weld rust, the colour of it, matched the steel over time. Like most RMS bridges, a full trial assembly was required. Both pestles and strongs were fully trial assembled within our Tomago facility, and this meant to replicate the exact same conditions as site, meaning we had a 100-long bridge fully erected within the shop. When that happened, it was a pretty cool thing to see. It was a full bridge under a roof in a workshop. The girders were fitted and assembled, and the site splices tacked to capture accurate measurement and dimensional tolerances. It also ensured that the site weld fit up was correct. All welding on the bridge was done by qualified personnel using WPSs. The bridge was surveyed by 2 independent contractors, and also the RMS team come out and did a 3D scan of the bridge. Once the trial assembly was complete, the individual girders were placed in our large blast and paint facility to be blasted to a 2.5 class profile. That included the outside surface, which isn't painted, and the inside surface has system SC5 applied. SC5 is a 3-coat system, and with the final top coat being white in colour. Once the paint application was complete, the girder segments were taken out into the yard and applied 3 cycles of fresh water. This was over a 3-day period, and the process is done to help and aid in the superficial rusting in a uniform manner. Finally, we need to transport the girders to site. Our logistics company and engineering team spent months of planning to transport these oversized girders to Berry, which is down in sort of the south coast of New South Wales. A route survey needed to be done and approved before any girder movements was allowed to happen. All this information was put into a transport management plan and reviewed by the site team to make sure that all transport boxes were ticked. We liaised closely with Downer Seymour White over a period of weeks to plan the girder arrival on site so that it got there at a specific day and a specific time, so that there was no impact on the large cranes which were booked and mobilised, and also minimal impact to traffic movement. The greatest challenge The greatest challenge is to ensure the girders were delivered prior to the Christmas break. Due to the road curfews, this was to overcome to ensure all permits, police escorts, etc. were all booked and approved within appropriate lead times to avoid any delays to the project. Once the girders arrived on site, we mobilised a 6-man team to do the final splice welding. For pestles, we were there about 10 days, and for the welding of strongs, I think it was around about 6 days. All splice welds were NDT tested to ensure that their structural integrity was sound. That's about it for the procurement, fabrication and welding of the bridges. It was a challenging project. It's been one of the most rewarding ones that I've been involved with since I've been here at SIDMEC. Thanks very much. Have a good day.
Thank you, David and Andrew, for those excellent presentations. We'd like to send our apologies for David Kukulevsky, who unfortunately is unable to join our today's session. So David Talbot will be providing an overview of his presentation. Please welcome back David Talbot.
Thank you, Georgina, and apologies everyone. David Kukulevsky's not feeling too well, so he's unable to join us today. So you'll have to listen to me for a little bit longer, talk about some of the construction aspects. So first of all, just a commentary on David. So at the time of the project, he was working for the construction joint venture, being JV between Downer and Seymour White. But since the project, David is now working for Transport for New South Wales. So a bit of a unique position, I guess, in being able to talk about both the construction aspects at the time and then from the client side, now that he's working with Transport for New South Wales. So just on the next slide, please. So as sort of noted a little bit earlier, so that was a Downer Seymour White construction joint venture. And the design was undertaken as a design-only contract between Transport for New South Wales and Arcadis. And then this was then let as a construct-only contract with that Downer Seymour White joint venture. So that was started for construction back in about 2018, with the Pestles Lane overpass completed around mid-2020, and then Strongs Road completed about mid-2021. Next slide, please. So I guess there's not too much to talk about from the construction aspects. Both, I guess, for weathering steel and normal steel, a similar sort of process, similar scope of works. So for the temporary works, the construction joint venture engaged Ridwood Consulting for the temporary works designs. So this is to help stabilise the girders just while they're being constructed. A Borgers crane, so a 500-tonne crane, was mobilised to site to lift the girder segments into place. And then, as Andrew mentioned, SIDMEC then came to site and completed the field splices. So once the field splices were completed, the bridge could then be lowered onto the permanent bearings, and then the rest of the construction works completed. As I mentioned, there's sort of not too many differences in the overall scope of works, but I guess the biggest thing, as we've sort of talked about it quite a bit here, is just that patina. So I guess making sure when you're storing the girders, when you're transporting them, installing them, that you're just taking care to look after that coating, because any sort of local damage is, you sort of want a uniform approach. So if a little bit of it is damaged, then it could colour differently at a different rate to the rest of the bridge. So that's it from me on the construction. I'll pass it back to Georgina, and then we'll go into the Q&A session. So thank you.
Thank you, David. I'd now like to welcome Rob Danis. He's a National Engineering Manager of Infrastructure at BlueScope Steel, and Rob will be joining us today for our Q&A session. So it's now your turn to get involved. Please ask our speakers questions via the chat box and who your question is directed to. And a big thank you to everyone who's already submitted their questions while registering. And I see a few questions have already come through already. So we'll get started. The first question is directed at you, Rob. It's from Paul in Tasmania. He's asking, the key areas for corrosion in steel are always at the joints and where moisture dirt can accumulate. How is this addressed with weathering steels?
Thanks, Georgina. Yes, that's a question I get asked quite a lot, and the detailing for weathering steel bridges is very important compared to standard painted steel bridges. And we have guidance on that, which David talked about in the presentation, was the HERA design guide from New Zealand. As when Arcadis were undertaking the design of this bridge, we hadn't actually made that available in Australia. So since then, we've actually commissioned this document, which is freely available from our website. And that basically highlights how you should design and detail correctly a weathering steel bridge. Like some of the things David talked about, grinding back the welds. You can put drip pans, drip plates to avoid any staining at the abutments. But if there is any build up of dirt or moisture during your inspections when you're checking the bridge, you can use things like a compressed air jet to blow the dirt away. Moisture can be washed away. So these procedures can all help address any of those problems.
Thanks for that, Rob. And another question, either for yourself, Rob, or David might want to jump in here, is how the product performs in a marine environment. And this question is from Ziavash. David or Rob, would you like to respond to that one?
David, do you want to go first? Or?
Yeah, happy to jump in first. I guess there is the guidance in that AS 5100 Part 6. So that has limits based on the aggressive nature of it. So in terms of where you're talking marine, so high chlorides, that sort of thing, then typically I would not recommend weathering steel. But again, it just comes down to the site and what you're looking at. So if you're talking about a fully submerged marine environment, then that's obviously not suitable for the patina formation. But yeah, site by site, I guess, and following that guidance. Rob, anything to add?
Just to add on that, David, I'd say so in the AS 4312 standard, which has all the various corrosivity zones around Australia, and following our design guidance, we would only recommend using it in a corrosivity environment of C1 and C3. So if it's in a C4 or C5 zone, the project, we wouldn't recommend the usage of weathering steel in that scenario.
Thanks for that, Rob and David. Another question is from Gavin in New South Wales. I might direct this one to you, David. He's asking which fasteners would you like to see available for similar constructions in the future?
Yeah, I think as Andrew touched on, I think it was harder to sort of supply or get a supply of the weathering steel bolts. I think having that, I guess it comes back to a little bit chicken and egg. I think as more bridges are used, then we'll see a more readily available supply of weathering steel bolts. But in the interim, I think for me, sort of, I guess, potentially coated stainless steel bolts or sort of non-bolting splices. But yeah, I think where possible, then those weathering steel bolts.
Just something slightly I could add on to that, Georgina. We've actually had some dialogue with Hobson Engineering last week, and they are pleased to announce that they will be making weathering steel bolts here available in Australia. So this is good news for future weathering steel bridges, which has just recently come to light.
That's good to know. Thanks for that, Rob. And thanks, David. Next question, I might direct this one to you, Rob, is how do you remediate future pitting that occurs on the weathering steel surface? So is there a pre-treatment recommended to help generate the patina prior to installation? And if so, what pre-treatment is recommended? And this question's coming from Benjamin in New South Wales.
So ideally, we don't want to see any pitting, but if that does occur, we can do some grinding back and welding of that to remove that. In terms of pre-treatment, this is definitely recommended after finishing the fabrication of the weathering steel structure. So after you've finished and given it an abrasive blast, you should then undertake a minimum 3-cycle process of wetting and drying the weathering steel structure. So that could be as easy as hosing it down, letting it dry, and repeating that 3 times as a minimum before sending the fabricated steel structure out to site, as that will help accelerate the formation of the patina as that continues to develop over time. But yeah, that's what we'd recommend at initial stage.
Excellent. Thanks, Rob. And a question for you, Andrew. This is from Nicholas in New South Wales. He'd like to understand the welding of mild steels and weathered products, and specifically the requirements for the electrodes.
Yep. This is a bit of an interesting question, especially at the moment. It's a bit of a hot topic. Both regular 350 and weathering steel have very similar welding characteristics. But in the current Australian standard 1554, there's a couple of requirements around the welding of weathering steel. For example, with single run fillets or butt welds, a standard consumable can be used, and that's because of the dilution that happens between the parent material and the welding consumable. And then they talk about multi-pass capping and multi-pass fillet welds. Due to the same reason, because of the lack of dilution, you need to use a nickel base consumable. And the reason it's a bit of a hot topic at the moment is because B201 has recently been revised, and they recommend using or specify to use all nickel wire. So that's for all runs, whether it be single or multi-pass. So it's something to keep an eye out on too.
Great. Thanks for that, Andrew. Rob, another one for you. How would you address graffiti if this is on the weathering steel? This is coming from George.
Yeah, we've had some interesting discussions on graffiti, Georgina. There's a couple of products which we've seen tested. So in the updated Hero Guide, they have a product they recommend called Peel Away, which is like a paste which you apply to the graffitied surface of the weathering steel, and you let it sit there for around 24, 48 hours, and then it hardens, and you basically peel it away, and that takes away the graffiti, and you don't lose any of the steel section after that process is done. But another product which we've also tested here at BlueScope is a product called Easy Clean. That's made by the Boxall Group, and that product basically you will apply the liquid product with a paintbrush to the graffiti, and you let it sit for a couple of minutes, and then essentially you just hose it off, and the graffiti washes away. So that we found to be probably the quickest and easiest form of removing graffiti from any weathering steel. And if you don't want to do anything, that's another thing. The patina will actually cover the graffiti after 5-7 years. So if it's not offensive, you could actually leave it as well. So there's a few options there.
Excellent. Thanks, Rob. David, we might go over to you now for a question. We've got a question from Abdul from Victoria. He's asking, the patina takes around 8, or you mentioned in your presentation, the patina takes around 8 years to form completely. Does that mean initially there won't be any protection for the steel?
Yeah, it's a good question. I guess that is, I guess in a case that is real. So the corrosion rate at the start is fairly high, and then as that patina forms, that corrosion rate, starts to decrease until it's fairly negligible after sort of 8 years or so. So yeah, it is unprotected steel at the start, and that's why we form that patina coating.
Yeah, the only other thing I might add there, Georgina, is because it's being used in corrosivity zone C1 to C3, the maximum section loss is only 50 micron per year, so that's what's fine. And in those areas, you wouldn't be seeing that much section loss anyway. So when you extrapolate that out over the 100 years, it's well within the tolerances, which, like David mentioned on buried abominary, I think they allowed 2 mil each face, so you might get 0.1 of a mil, over the 100 years in those areas. So that's where it does its best performance anyway.
Thanks for that, David and Rob. David, another one for you. This is coming from George. He's asking, how could the weathered steel versus normal steel be a shallow construction depth benefit?
Sure. So I guess just in my presentation, I commented on the shallower depth. That was more in relation to compared to a concrete section. So Yeah, agreed. There's very little strength, or there is no strength difference between weathering steel and other sort of carbon steels. So no, that comment or that point in the presentation was in relation to comparison against a concrete structure.
Thanks, David. Andrew, we might go back over to you now. There's a question here from Nicholas in Queensland. He's asking what potential changes to construction techniques would be required in order to manage the innovation during the build phase.
The constructability, it doesn't change between a normal 350 grade or a weathering steel bridge, from what I understand. Innovations in the build phase, I think the focus is on the external surface and damaging or trying not to damage the patina. So for us, when we do weathering steel projects, we try to make sure that we have jigs and assemblies and come up with innovations to try to remove, I suppose, any chance of damaging that external surface. That might be from, I don't know, stopping us from putting dogs or wedges on the outside, or tacking something to it, a brace or a stay. So the innovation side of it would be about knowing how to manage the external surface. Internally, there's no real difference.
Thanks for that, Andrew. And a query here for you, Rob. This is from Luke in Queensland. Luke's asking, what do you think are the biggest challenges for uptake on weathering steel on large-scale bridges? There seems to be an extremely valid case for 100-year life in comparison to coated steel in suitable environments.
Yeah, I think that's what makes weathering steel a much more viable option for those infrastructure projects moving forward here in Australia. As one of the issues has always been with painted steel bridges, you've got to recoat it, maybe 2-3 times over the lifespan of the bridge, and weathering steel removes the need for that. So, from a maintenance cost perspective, it should work out a lot cheaper, as you don't need any of that additional temporary scaffolding, road lane closures when repainting or stripping back paint from an existing bridge. And that's also producing some environmental benefits as well. No containment particles need to be worried about volatile organic compounds when recoating existing painted steel bridges. So I think just having more of these sessions will help give people more awareness and familiarity with it moving forward.
That's right. Thanks for that, Rob. And another one for you is how maintenance costs could be reduced by using weathering steel in bridge design. This is from George in the USA.
I guess similar to what I was just saying, as long as you're designing and detailing it correctly, like David's highlighted in his presentation, to prevent any potential, maintenance issues with dirt and moisture, following the correct detailing that we cover quite extensively in the HERA design guide, which is now available here in Australia. Following all those best practices should essentially be able to deliver you a very low maintenance bridge solution in weathering steel.
Sorry.
Thanks for that, Rob. Another one for you, David. This is from James O'Connor. He's asking, and I think you mentioned this in your presentation, did they paint the inside of the girders and why?
Yes, so the internal surface was painted. I guess there is an argument there to be made that the internal surface could be left unpainted, and particularly some areas of it. But I guess a couple of little items to pull out of that. The top surface of the top flange, so that'll be in contact with the concrete deck. So having that painted and isolated is of advantage, because you're not going to see that patina forming there. And then I'm not sure if there's some other questions on this, but also the potential for microclimates to form. So there are ventilation outlets in the girder, as well as access for future inspection. But there is still the chance that a microclimate could form inside the girder, which may impact the formation of that patina. And then I guess finally the white paint. So the choice of that white paint, it means that when you're inspecting, you can sort of more readily see any issues. If it was the patina inside and you're in there trying to have a look around, it could be very hard to spot any issues going on. So, yeah, I guess they're some of the drivers for why that internal surface was painted.
Thanks for that, David. And another one for you, you probably already touched on this with the detailing that you covered, but doesn't the rainwater become red-brown when dropping off weathering steel?
Yep. Yes, so it does. I guess that's part of it as to why we try and prevent water getting there in the first place. But in some of those details, so at the bearings or above piers, where you may see staining otherwise. Again, just those particular details to just prevent that water from causing those issues. So drip pans to protect bearings, or whether it's directing the runoff away from the faces of concrete elements, just so that you avoid that staining. But yeah, it does become that red brown. I guess it's also more prevalent at the early phases. As it sort of darkens and the patina forms more solid, you're going to see less and less of that as well.
Thanks, David. Andrew, a question that's popped up for you. Was a test well destructively tested? This is coming from Adrian. Oh, you might need to unmute.
Sorry, I was on mute. If that's the test well that was sent down to site, no, it wasn't. That was just purely for understanding how the colouring would happen between the material and the weld. But as for all the welds on the WPSs, yes, they were destructively tested, and then NDT was carried out on all the other welds within the bridge.
Thanks, Andrew. And a question for you, Rob. Is this the first time Transport for New South Wales have adopted a weathering steel bridge?
Yeah, that's right, Georgina. That was the first one that Transport New South Wales had undertaken. So we actually worked quite closely with them during the specification of the bridge, giving them as much information and helping them determine the suitability for it, being their first in Australia. But having said that, since then, there's been another one built out near Parramatta Way at James Roos Drive, the Parramatta Light Rail, which is the longest weathering steel light rail bridge in Australia. And there's also another one going in at the Sydney Gateway. And there's also a couple potentially in the pipeline with Transport New South Wales. And what we're actually doing quite a bit of work with them on putting weathering steel samples out at future project locations, which are in high C3, low C4 corrosivity zones. So we can capture at least 12 to 24 months of data for them before these projects come to light to determine suitability in some of these really urbanised locations where going back to try and repaint a steel bridge will be extremely difficult.
Thanks for that, Rob. Andrew, another question for you. This is quite an interesting one. What happens if the bridge is struck by an overhyped vehicle and the weathered steel girder is damaged? Is there any acceptable repair treatments for weathered steel?
I think this actually did happen down on Pestil's Lane, which was the first bridge we installed. It was struck. It was struck by a bit of earth-moving equipment, I think. The remediation was to blend it. It wasn't hit too hard, so you could actually just blend it and sort of fix it up and then just give it a bit of a brush. But if it was to be hit hard, I would imagine that you'd have to repair it with weld, then blend it off, and then you'd probably have to blast it using garnet or a shot of some sort, and then you'd have to use the 3 cycles of water as well. So much similar to how we do it in the workshop, you'd probably have to do that as a repair process.
Great, thanks for that, Andrew. David, a question from you from Stephen. Were the bridge girders supported on elastomer bearings? If not, were steel bearings used? And did the bearings need any additional protection from a corrosion perspective? Or were they isolated from the girders due to being dissimilar metals?
Yep. So yeah, again, a good question. And I guess this comes into play wherever you have, dissimilar metals or or different environments. So for the bridges at this site, we used steel pot bearings, so not elastomeric, and that different metal was isolated from the weathering steel. So there was a sort of a layer of isolation between the two.
Thanks for that, David. And a question for Rob. This is from Andrew. On a steel plate, the design may be subject to the type of welding, and it might need to the steel plate be a Z grade plate. Is the weathering steel plate have a Z graded? What will be the cost difference?
Thanks, Georgina. I can't say anything about the cost difference because that's what our distributors would be able to give you information on that. But weathering steel is available in Z graded plate if required. So just need to specify that, and that can be something that's made available if needed for your project, which you've actually supplied Z graded weathering steel on other projects as well.
Great, thanks for that, Rob. David, we just have a general question about what was the deck constructed of, or what was the deck construction type?
Yep, sure. So the steel boxes, the main boxes, they were obviously weathering steel, and then there were some precast reinforced concrete deck panels that were laid down, and then some in situ reinforced concrete deck was then poured. So that was sort of the materials made up of steel with a reinforced concrete deck.
Thanks, David. And Rob, back to you. Question from Mark Riddick. He's asking, how do you go about specifying weathered steel?
Okay, yep. So we have quite a bit of information on our website at steel.com.au, which covers all of the plate sizes, lengths, and availability in thicknesses of weathering steel. So basically for bridges, it comes as WR350, L0 and L20. And we do have thinner gauges from 3mm to 6mm for architectural cladding. And all that information is available on our website. And if you need any help on that, please contact BlueScope and we can help you with the specification as well.
Thanks for that, Rob. I think that pretty much finishes up the questions that were coming through. So that's all we have time for today. But I'd like you to join me once again in thanking David Talbot, Andrew Sams, and Rob Dennis for their time and input today. And I'd like to thank Engineers Australia and their industry partner, BlueScope, for their support. And if you could please complete a short feedback form, which is found in the description box below, to help us improve and plan for future sessions. And thank you again for joining us, and we hope to see you at our next Thought Leaders event.